Hello, everybody. In this video, we're going to talk about randomness and computation, and a little bit about pseudorandomness, and we'll see what this means shortly. So we discussed the idea of resources of computation. In general, complexity theory tries to understand the power and limitation of different resources of computation, and also their trade-offs. So we talked about memory versus time. Can you, for example, have algorithms that use less time if you allow more memory? And so far we discussed a few resources, perhaps some of the major resources, mostly time. We also discussed memory, space. We also discussed access to the input, read once versus random access, which we didn't discuss in this class. So the way the input is given to you does give you some kind of power. So in a sense, this is a resource of the computation. We discussed communication complexity, but there's much more. And today, I want to discuss one other resource. I would say that a very highly recommended class is CS254, where you can learn much more about complexity theory, and in particular, some of the topics that we are discussing in the last videos of this course. So in this video, we're going to discuss randomness as a resource. So randomness is the ability of a computation to flip coins, to make a decision based on a coin flip that is unbiased. So we discussed algorithms that can make choices non-deterministically. So they, in a sense, they're making the best choice. With randomness, we mean that you can make a random choice. You can flip a coin, and if it's 0, you do one thing. If it's 1, you do another thing. I'm going to discuss mostly examples where randomness is useful, but a very important topic is derandomization. So these are examples where we may naturally use randomness, but this randomness can be reduced or eliminated altogether. So this is where randomness is less useful. And the basic tool for derandomization is this notion of pseudorandomness. Objects that look random, look like they're uniformly distributed, but in fact they are not. We won't discuss pseudorandomness as much, and definitely not as much as it deserves. It's one of the most beautiful and most powerful topics in theory, and it affected essentially every area in computer science. So randomness in computation. There are places where we can prove that without randomness you can do nothing. Examples are, and we'll discuss all of these examples, come from distributed computing, when you're making a computation between different entities in a distributed environment. Cryptography, where sometimes even the mere definitions, the definitions that we want, need randomness in them to make sense. And other areas like sampling and simulations, which require randomness. There are other areas in which you don't have to use randomness, but using randomness makes a huge difference. In fact, we've already seen one such example or two such examples in communication complexity, where equality is a very efficient randomized protocol, but doesn't have a good deterministic protocol, and we had another example in streaming. I will also show you another example here about routing, a beautiful idea due to Leslie Valiant of how to reduce congestion in a network dramatically with a very simple trick. And finally, there may be places where randomness is not needed at all. And this is mainly in algorithms. So if you have an algorithm that runs on some problem in your own computer, like a Turing machine, the question is, can a Turing machine do anything better with randomness? So often the best algorithm is randomized. But the question, is it really needed? Can you always de-randomize it? We gave one example of an algorithm that de-randomized a randomized algorithm. That's the algorithm for primes in P, which I mentioned was based on a randomized algorithm in polynomial time for primes that was de-randomized. De-randomized means turned deterministic. This kind of gives rise to two questions. So we know about the P versus NP. This gives rise to two other very important questions within complexity theory. One is the BPP versus P, which without getting into the definition means BPP equals P means that every randomized algorithm can be de-randomized, and the cost in terms of time will only be polynomial, some polynomial factor. So perhaps if you have an algorithm that runs in times t and it's randomized, perhaps you can have a deterministic algorithm that runs in time t squared. The counterpart of this question is the RL versus L problem. And this is whether randomized algorithms can be de-randomized without increasing their memory by more than a constant. So perhaps a randomized algorithm that uses 10n memory can be de-randomized, and now it will use 100n memory. And in fact, we believe that both of those are true. And this is where derandomization, where pseudorandomness comes into play. We won't discuss it much. So let's start by giving some examples about the power of randomness. And we mentioned distributed computing as being one area in which randomness is important. And let me mention one example, and this is the famous dining philosophers question. You have these philosophers, they're eating perhaps with the chopsticks, and they have between them in this round table, there is a chopstick to your right and a chopstick to your left. You need both of them to eat. And at every given point, you may turn to the right and try to grab your chopstick, or turn to the left and try to grab the chopstick to your left, and you need both of them. Problem is, what happens if all of them are hungry, all of them turn to the right, take their chopstick, now go to the left, and they see that the chopstick is used, so they cannot eat. But nobody can eat. So perhaps they go back to the right and release their chopstick and go back to the left and take this chopstick instead. And now they go back to the right, and again, this chopstick is missing. So the dining philosophers may starve forever if they're using a deterministic algorithm. But if they're using a randomized algorithm, they can eat very frequently. So every time that they want to eat, they will choose to look to the right or to the left randomly, and this will break the symmetry that we were worried about. A different example is that of Byzantine agreement. You have a group of Byzantine leaders, and they want to decide whether to attack or not to attack, but they only want to attack if all leaders want to attack. So they are trying to exchange information and to make a decision, a joint decision. And perhaps we want it to be the case that if all of them want to attack, they will attack. If all of them wants not to attack, they won't attack. And in between, they can do whatever they want. Turns out that there is a huge difference between deterministic and randomized algorithms or protocols. So if and the problem in this protocol is that some of these Byzantine leaders may fail. Think about a computer that is broken, perhaps even malicious, and there is some malicious software on it. So if you have a synchronous protocol that has T failures, deterministically to reach an agreement, they need T plus 1 rounds. In a randomized fashion, they only need a constant number of rounds of communication. If it's asynchronous, and this is very realistic, they don't have the same clock. They cannot say, okay, now all of us are doing this, and the next round all of us are doing this, because my next round may come later than your next round. Then Byzantine agreement is impossible deterministically, but possible with a randomized protocol. We already discussed this idea that randomness saves communication. For example, Alice and Bob may have a copy of a file sitting in different areas, and they just want to make sure that the copy is identical, perhaps that it didn't get corrupted. Deterministically, you need to send the entire file. If you have some randomness in the sky that both of them see, then you only need order 1 bits of communications, or if you want to get error that is smaller, then log 1 of this error that you want. And with private communication, you need logarithmic number of bits. And we've seen this example. So this is, in a sense, a derandomization of this randomness in the sky example. In cryptography, randomness plays a crucial role in all levels. First, for defining this notion of keys, private keys, if there is no randomness, then there is no secrets and no identities. If there is no randomness, then every entity can simulate every other entity. They are deterministic. Encryptions, we want 2 encryptions of the same message with the same key to be different, because we don't want anybody to notice that I'm sending the same message again and again. And this is very important. This is what's called semantic security. And to define it, you need this notion of randomness. Deterministic encryptions cannot obtain this property. Deterministic encryption of the same message with the same key would always be identical. So in fact, you need a randomized encryption. And we talked a little bit about randomized proofs that are very powerful, and they give rise to this notion of zero knowledge proofs that is amazing. We'll talk about pseudorandomness in the context of cryptography, and actually not only randomness is important, but pseudorandomness and strong pseudorandomness is also very important. Random walks and Markov chains. An amazing thing is that if you're walking in a graph, walking in a maze, and you flip coins, you can get out of the maze, as long as there is some way to get out of the maze or get to any other point that you're connected with. So this is a way to explore a graph without needing much memory. You don't need to know more than the current location and how many steps you took so far. This is also the basic of many algorithms, important algorithms, that rely on the fact that a random walk converges to some stationary distribution, an interesting stationary distribution. And this is also a way to do sampling. For example, if you want to estimate the size of the web as it comes into account in some web search server. And also it allows you to simulate physical systems that do have some randomness in them. So this idea of random walks is extremely useful, have been used all over. Let me give you this example of that we're thinking about shaking the input. So one way in which you are using randomness is to turn a worst case behavior into a randomized behavior. And this randomized behavior, randomized input, may be much better. So imagine a communication network that is an n-dimensional cube. So every node has a bit string, let's say log n bits, and two nodes are connected if they are identical, if their bits description is identical up to some one point. So in particular, the node that has the that its name is 00000 is connected to 10000 or 01000. It's connected to every other string with exactly single one. And similarly, every string is connected to every other string that you can get by changing a single bit. And this is just one example. In fact, this idea goes much further. So it turns out that if you want to send, imagine a situation where every node in this graph wants to send a message to some other node. And this is a permutation. So it's not that all of us want to send to the same node, each one of us wants to send to a different node. It turns out that in the worst case, over this permutation, given every deterministic routing scheme. So the routing scheme says if I want to send a message from my node to another, here is a path that my message will take. Whenever this path is deterministic, there will be a busy link, an extremely busy link. Essentially, a substantial fraction of all the messages will need to go through a single edge, which will create a huge slowdown. So this is congestion. And a brilliant idea by Valiant was to say, assume that I want to send a message and I'm at X and I want to send a message to node Y. Instead, what I'm going to do is send my message into a random location, Z, and from there, the message will go to Y. And the way I'm then sending the message is through the most simplest path possible. The path that kind of goes from left to right and correct every bits that need to be corrected. So I want to send my message to Y, but instead I'll first send it to Z, which is random, and then I will send it from Z to Y. Turns out that this way, the congestion that we expect on every edge is a constant, which is quite amazing. And the idea is that whenever everybody's sending their messages to their own random Z, these messages are sent to a random location. And then in the second part, they are sent from a random location. So there is no bad permutation. Every permutation from X to Y turns that may be bad is turned to two random permutations, one from X to Z and one from Z to Y. So now the expected load on every edge is going to be order 1. Another example is this randomized quicksort. For those who already took CS161, there is a very simple, efficient algorithm for sorting, which is known as quicksort. And it has a deterministic version that would work usually. But in the worst case, it will be very bad. And randomized quicksort is as if you first take your input and kind of switch it around. So you take your input and you want to sort it, but instead you permute it in a and in a random way, and then you sort it. And then the worst case input becomes a randomized input, which you can deal with. And finally, let me mention that there are various algorithms that that work in practice, but in the worst case, they have a horrible behavior. There's an entire field called smooth analysis that says that these algorithms perhaps work very badly in the worst case. But if you take every input, even the worst case input, and you perturb it a little bit, then the algorithms will work well. So this kind of explains why these algorithms work well in practice. The last example that I want to give is private data analysis. You have a data set and you want to run some statistical query on your data set. And if you run these statistical queries on the data set, perhaps it's a sensitive medical data set. If I allow you to run exact statistical queries, then you can learn sensitive attributes of individuals. So you can learn a particular sensitive property. If some individual has some medical condition. But with a little bit of randomized noise, it can be shown that you are secured from that. So if instead of giving you exact answers, I give you answers and then I perturb them a little bit, you will not learn the sensitive data. This is the basis of many algorithms in what's known as differential privacy, which is a beautiful concept that I wish I could tell you more about. So I mentioned pseudorandomness. There's tons of things to say about actually most of the examples that we discussed so far, and also about other examples like algorithms for routing and data structures. All of them use derandomization on a very, very foundational way. I want to give you one example of pseudorandomness, and that's in cryptography. So there is this notion of one-time pad. The notion of one-time pad that you have some plain text. It's a sequence of bits. Here, for example, it's 000111111. You put it into encryption. The encryption has a key, a secret key, let's say 011001000. And what you do, what you send to the other party is not your plain data. You XOR, you bitwise XOR each bit of the plain text with each bit of the key to get a bit of the ciphertext. XOR bit by bit means that if it's just the parity of the bits. So if both bits are 0 or both bits are 1 in the key and the plain text, then you output a 0, otherwise you output a 1. Now, when the other party gets it, they want to decrypt it to get the plain text. They also know the key, and they just XOR again the ciphertext with the key to get the plain text. This is a very basic notion in cryptography. It's in Shannon's work, trying to understand what's the size of keys that are needed for encryption. And it was actually used. So in the days of the Cold War, the US and the USSR have shared huge keys that they use to exchange messages. The security of this approach relies on the fact that you're not reusing the same key twice. Every time you send a message, You need a key which is as large as the message you're sending, and then you get rid of it. And so they had CDs full of random bits, and they use it for the communication. This is, of course, not realistic these days when you exchange messages encrypted with parties you never encountered before. So one basic idea towards making it more practical is a pseudorandom generator. So the pseudorandom generator will take a small key and will turn it into a larger key. The small key is going to be completely uniform. The large key is what's known as pseudorandom. Pseudorandom means that you cannot distinguish it from random, meaning that if you show an algorithm that is computationally bounded, perhaps polynomial time, a key that is either completely random or the output of this pseudorandom generator, they cannot tell which is which. If you remember this example of Pepsi versus Coke, in this blind testing, you would not know if you're getting a random string or a pseudorandom string. This is the definition. And given that you already get still a private key encryption, but much more efficient. This also comes into, so far we're talking about randomness, which is a resource of computation, perhaps an unexpected resource of computation, perhaps people that did not think about it would not imagine that using randomness can make a difference. If an algorithm is like a recipe, why the hell would you use randomness? Imagine a cake where you flip a coin, and based on the coin, you either put 1 glass of sugar or 2 glasses of sugar, cups of sugars. Then it just doesn't make any sense. But in algorithms, it does make sense. What this example also shows is that the computational lens changes a very basic notion of randomness. So if you look information theoretically, you cannot take a random string and make it to a larger random string, uniform string. But if you take computation into account, you can take a short random string and make it into a longer string that is effectively random. It is pseudorandom. So taking the computational limitation of the observer into account changes this notion of randomness, this notion of entropy. I've heard the statement from a person that works in the field that pseudorandom generators are in fact, in some sense, the most basic element of cryptography, in the sense that without pseudorandom generators, also almost nothing works. So if your pseudorandomness is bad, almost all of your crypto will fail. And with it, you can already do something that's not trivial, like this. So I will not discuss any more about pseudorandomness. It's a beautiful field. Accidentally, it's one of my main fields of study. Let me kind of, as parting thoughts, mention that we have shown that randomness is both very powerful. There are places in which without randomness, you can do nothing, and with randomness, you have very strong solutions. And it's also weak in the sense that in many other areas, you can probably replace randomness with pseudorandomness and essentially get rid of it. And if you'll get more into complexity theory or even other areas, you will see that randomness and pseudorandomness play an important role essentially everywhere within computer science. Thank you.